Hello friends, today's question. A small spherical monoatomic ideal gas bubble with gamma of 5/3 is trapped inside a liquid of density ρ1 as in figure. Assume that bubble does not exchange any heat with the liquid. The bubble contains n mole of gas. The temperature of the gas when the bubble is at the bottom is T0. The height of the liquid is h and the atmospheric pressure is P0, neglect the surface tension. So we have these three, you can say, sub questions based on this main one, and this is the figure. So we have a liquid of height h and a bubble which is at a height y from the bottom of this tank, and P0 is the atmospheric pressure. So in the A part, we are supposed to find out as the block moves upward beside the buoyancy force, the following forces are acting on it. So in this case, there are, you can say, a combination of three forces other than this. First one is force of gravity, then the pressure, and then the liquid, force of viscosity. So all these three permutation combinations are given in these four options except the buoyant force. And it states that as the bubble moves upward, so it means we have to find out as the bubble is moving upward what are the different forces that will be acting on it. So let us analyze these options one by one. So first of all, let's note out that what are the different forces that will be acting on this bubble. First one will be we can say that bubble moves upward various forces acting on it, various forces acting on it. So let us, first one will be the gravity. And that will be obviously acting downward. Second will be the buoyancy. And that will be acting upward. But it is given a question that we have to ignore this particular force, so we are going to ignore this. Third will be our pressure, and this pressure will be from the liquid, from all the sides, pressure on the bubble, due to liquid. And this pressure, as bubble is approximately at the center, so this bubble, this pressure, liquid pressure rather, will be acting from all the directions equally to this bubble. So we can say that pressure exerted by the liquid by the surrounding liquid rather by the surrounding liquid acts equally from all directions. So therefore, this particular, we can say, force, that is because of the pressure on the bubble, will not be contributing in any direction of the bubble movement. So you can see from here, it does not create a net force in any direction. So because of this pressure, there is no net force in any direction. So we can make a conclusion that it does not contribute in motion of the, you can say, does not contribute in downward or upward force on the bubble. Downward or upward force on bubble. So right up till now we have discussed three forces. So only the gravity is the individual force up till now which is acting on the you can say bubble. So let us, there will be also the fourth force, and that will be our viscous drag. So viscous drag, and it will be, you can say, viscous drag is because of the viscosity of the liquid. So as the bubble is moving upward, viscous drag will oppose this motion of the bubble. We can say as bubble rises, it encounters resistance from the liquid. In the downward direction. In the downward direction. So we can say from all these four forces, gravity is one of the force that is acting on the bubble. Buoyancy, in the question it is said that we have to discuss beside buoyancy. So gravity is not the alone force due to pressure on the liquid. So we just make a conclusion that on this third, that it doesn't contribute any net force. So obviously this cannot be one of the options. And the third is force due to gravity, and it also includes the force due to pressure of the liquid. So this can't be also the option. So we have only last one, D, which states that force due to gravity, which is one of the option, the correct option. Another one is the force due to viscosity of liquid, which is our viscous drag. So option number D is the correct option. You can say option D is correct. So this completes the part A. In part B, it says that when the bubble is a height of y from the bottom, its temperature is. So we have to find out the temperature of the bubble at a height y from the bottom. And you have to keep in mind, it says that bubble does not exchange any heat in the liquid. Okay, so it means it is an adiabatic process. So we start for part B. So we start from the statement that since the bubble is moving without exchanging heat, it undergoes adiabatic process. It undergoes adiabatic process. And we can write the equation for that also. So we can say P V raised to power gamma is a constant, and value of gamma is given as 5 by 3. And this is the first information from the question. And the second information is that we can find what will be the pressure at the height y, or we can say at a height y from the bottom. So we have to find out the pressure at this particular point, and let us call this as pressure at y. So let me draw this figure approximately. So this is our, and we have a bubble here somewhere. Total height is given as h, capital H, and the height of the bubble from the bottom is y. So from the top it will be h minus y, and there is atmospheric pressure, and it is given in the question itself, it is given as P naught. So we can say that pressure at a height y from the bottom, pressure at the height y from the bottom let us call that Py. Okay, so we are going to say that pressure at this point is our Py. So Py will be equal to atmospheric pressure plus pressure due to column, liquid column, pressure due to liquid column of height h minus y. Atmospheric pressure is P naught, so we can say P of y will be equal to P naught plus rho L, density of the liquid, G and the height h minus y. So this is the pressure at this height y from the bottom. And in the question itself it is given that you can say the pressure at the bottom, because it in the question it's mentioned the temperature of the gas at the bottom is T naught. So next we find out initial condition at the bottom of the liquid. Initial condition at the bottom of the liquid. So at the bottom, y will be equal to 0. At the bottom, y is equal to 0. Therefore, the pressure at the bottom, let us call that as PB, and in this case this bubble is at the bottom. Now the total column height is h and the atmospheric pressure is still P0. Therefore we can say that this will be P0 plus density of the liquid G multiplied by h. And it is also given that the temperature at the bottom is T0. Temperature at the bottom is our T0. So therefore we can say that for adiabatic process we can extend this, because as the process is adiabatic, and we also say the pressure at the bottom is T0 and temperature at the bottom is T0 and temperature at the height y from the bottom let us suppose is our T1. So with respect to adiabatic condition, we can write that for adiabatic process, we can say ratio of the temperature at y will be to the ratio of T0, that is at the bottom, will be equal to pressure at the height y divided by pressure at the bottom whole raised to power gamma minus 1 divided by gamma. So from here we can just write it that temperature at the height y will be equal to T0. We substitute value of pressure at y, and pressure at y is our P0 rho Lg h minus y. So this comes as P0 plus density of the liquid G h minus y, and divided by pressure at the bottom. Pressure at the bottom is P0 plus rho L G H and whole raised power, it is, we can say gamma is given as 3 by 5, 5 by 3. So we can solve this. So we have 5 and this is 5 by 3. So this comes as 2 by 3 and this comes by 5 by 3. So this is equal to 2 by 5. So we can write this as raised power 2 by 5. Okay. So if you check the options that are given to us, we can clearly see that option number B is the correct option. Okay, it is our T naught, P naught plus rho Lg H minus Y. Yeah, so this is our temperature at height Y from the bottom. So option number B is the correct option. Option B is correct. Now we come to the our, you can say, third part, C part, which states that the buoyancy force acting on the gas bubble is, assuming R is the universal gas constant, so we have to find out what will be the buoyant force acting on the gas bubble. Okay. So we start with part C. So we say let the volume of the bubble is V. Volume of bubble is V, and it is given that bubble contains n moles of the gas. It is given in the question itself. It contains n moles of the gas. Bubble contains n moles of gas. So therefore, we can write the ideal gas equation. Ideal gas equation, which gives us that PV is equal to nRT, and here P is our pressure at height Y, which we denoted as P of Y, and T is the temperature at height Y, at height Y from the bottom, and T is temperature at height Y from bottom, which we denoted as T of Y. So we are going to modify this equation, and in this case also the volume of the bubble is V. So we can say that this V now can be written as that V is volume of bubble at height Y from the bottom. So we can write this as V of Y. So therefore, we can modify this particular equation with respect to the variable Y, and from here we can write that our V of Y will be equal to NR. We have T of Y divided by P of Y. Now we are supposed to find out the equation for the buoyant force. So now we try to modify or try to find out what will be the equation for our buoyant force. Okay. Buoyant force. So basic definition of buoyant force we are going to, basic concept of buoyant force we are going to use here, which states that the buoyant force acting on the bubble is equal to the weight of the liquid that is being displaced by the bubble. The buoyant force, so we say the buoyant force, and if we represented it as FB, acting on the bubble, is equal to the weight of the liquid, displaced by the bubble. Displaced by the bubble. Let us write this formula. So we can say our buoyant force FB will be equal to volume of the bubble, multiplied by density of the liquid, and multiplied by G. So we substitute the values. So you can say our FP will be equal to volume, we said will be our V of Y. Density is given as liquid is rho of L multiplied by G. And we substitute value of V of Y, which is equal to NR T of Y divided by P of Y multiplied by density of the liquid and multiplied by G. Now in this equation, now we are going to simply put the pressure equation, that is our P of Y, and we are going to put T of Y. So this is our equation for T of Y, and we found out what is our P of Y, which is given by this equation. So let me write both equations here only. We can say but P of Y is equal to P naught plus rho L G H minus Y, and T of Y, that is the temperature at you can say at a distance, at a height Y from the bottom, which we found out is our T naught, and this is our P naught rho L H minus Y divided by P naught rho L and GH and whole raised power 2 by 5. We simply substitute these two in FP equation, buoyant force. Now it is a simple calculation. FB will be equal to, we have this NR, and this will be coming as now T naught rho L G, and we have here, let me write T naught first, T of Y rather. So this will be coming equal to as P naught plus rho of L H minus Y divided by P naught plus rho L G H, and this is whole raised to power 2 by 5 divided by, and we have this our P of Y is our P naught plus rho L, and we have G H minus Y. So let us, because we can see from here that the denominator and the numerator of this particular fraction looks identical. Okay, so we can just make some adjustment here. This gives us NR T naught rho L G, and this comes in the denominator, so this will be P naught plus rho L GH whole raised to power 2 by 5. This goes into numerator, this becomes P naught plus rho L H minus Y, rho L, I think G I missed out here, I think there should be G also, 1 second, yeah, G is missed out, so this will be G and this will be G and this will be G. Yeah, now it's complete. And this comes as 2 by 5 minus 1. So we can say this will be equal to, this will be 2 by 5 minus 1, so this will be minus 3 by 5. So we are going to take this into the denominator. We have n r T naught rho L G, and this becomes now 1 upon, because this part is our minus 3 by 5. This comes in the denominator. Now this becomes P naught rho L GH whole raised to power 2 by 5 and multiply by P naught rho L G H minus Y whole raised to power 3 by 5. So this is the value of the buoyant force. So let us check what are the options that are given to us. Okay, so in the numerator we have only two options, that it will either B or D, because in the numerator we have only this particular value, and the only difference between B and D is the power of their respective equations. So H minus Y is having a power of 3 by 5. So the option number B is the correct option. So you can say option B is correct. So this question no doubt was a little bit lengthy to solve, but if you look at the question carefully, we have used every, you can say, parameter or variable that is given to us or information that is given to us in the question, and we get the final answer. So this completes the question. Thank you.